All right, here we go. So last time in the sense of the last thing that y'all saw in this course, sadly I wasn't able to be here. Thanks for y'all's flexibility in dealing with my illness. The very last part of the recordings that y'all watched was about change of variables and the big picture strategy behind the method of change of variables. The idea is that it's a ripoff of the idea of a substitution. It was suitably interpreted. Right? So we typically think of a substitution as something that allows us to turn, an integrand that we don't like for whatever reason because it's unfamiliar. I don't know how to actually find an antiderivative of that. How do we turn one integrand into a truly different integrand? And maybe this is something that I can integrate more easily. And that's nice, but I'm pushing it here as a method for taking an integral on one domain, right, and then reinterpreting it by way of this pullback strategy as an integral over a different domain, right? So with that point of view, and it's just a matter of how you choose to look at substitutions. With that point of view, we can kind of apply the same idea for double integrals, and the big upshot is that if you have a domain that is the image of a different domain, then you can do this thing, morally equivalent thing, where you do what we call the pullback, right? And so an integral that was originally on this original green domain gets rewritten as an integral now on what I'm going to call the pullback domain or the UV domain, or whatever you want to call it. I kind of like pullback domain. Okay, so that's the big picture idea. We turn integrals on images into integrals on the pullback. Okay, so with that said, the details, of course, and there's a bunch of discussion about what the stretching factor is here, and the stretching factor is conveniently denoted by this notation down here at the bottom. Don't forget what that represents. It's this absolute value of the determinant of the derivative matrix. And armed with that, now we're going to see our first example. So here we go. In fact, I'm going to zoom in a little bit more here so we can focus where I want to focus. Here's the question. We are given a domain that's defined as follows. I start with the unit square in the UV plane. So it says right there. And then we're going to look at the image of that unit square in the UV plane. Specifically, the image is going to be some set in the XY plane. That is our domain. That is the domain for our integral. And that image, of course, now it's going to be some weird shape. It ends up looking something like this, as it turns out. But this G function, this what's going to eventually be our change of variables function, it's not linear. Right, this G function is all kinds of weird. Let me see right there. So thus the contorted shape. Now, what is the point to changing the domain? Why is it that I consider this domain over here to be undesirable, but this domain over here is so great? I mean, why would I want to do a pullback? Why would I want to turn that integral into this integral? And it's because of where the corners are in this case. For example, if I were to take any sort of a slicing process of this domain here, right, this green domain, our original D given domain, I'd be slicing along, and then I'd slice through that corner. And then I'd have to start a new integral and keep slicing along. And then I'd slice through another corner. And then I'd keep going until finally ending. So I'd have to do 3 separate integrals on this domain on the right. Okay. Whereas, by comparison, it's pullback. This pullback over here in this case is not only a rectangle, it's a square. And not only that, it's the unit square. It's about the best domain you could possibly hope for a double integral. So big payoff for doing this. So we're going to do the pullback. Again, we were given the integral we've been asked to compute is an integral over here in the xy plane. So we're going to wave the magic wand of change of variables and pull that back, right? And be much happier working with an integral over here in the UV plane. Everybody on board on the strategy and the motivations? Does that make sense? Okay. All right, so now we got to worry about the mechanics. We need to know what the stretching factor is for our change of variables function. And we have a formula, right? This is straight up plug and chug. Here's the stretching factor. Right, so take a deep breath and start going. Let's see here. Now we have, here it is. Okay, here is our change of variables function. Specifically, note that this means that x is that formula right there, and that y is that formula right there. So when I, say we're going to be computing the partials of x and y to make up the derivative matrix, these are they. These are the things we're taking the partials of, and yada yada yada. Y'all can do the partial derivatives. Do keep in mind you do have to keep those partials. The organization of the derivative matrix has to be just so. Don't actually accidentally write down the transpose. It won't make a difference in the determinant, but it does make a difference in the validity of the argument. Right? So careful with that, as always. And it turns out this is our what I like to call Jacobian determinant. Now, of course, the issue here, the sticky wicket, is that we need to take the absolute value of this Jacobian determinant. This, the determinant of the derivative matrix. Is this thing positive or negative? Nasty question. Very concerning. How do I decide if this thing is positive or negative? And it can be an ugly matter. It could be that this expression is, for some values of u and v it's positive, and for other values of u and v it's negative. That's possible. In other examples, that could work out. If that happens, then it's a nasty problem, and it still might be worth it to do the change of variables, but you will have to do two separate integrals. You'll have to do one integral over here, where the stretching factor is the Jacobian determinant, and a completely different integral over here, where the stretching factor is being the absolute value, therefore the negative of the Jacobian determinant. So that's a little annoying. The good news is that is not what's happening in this case. And in this case, we can understand the sign of this Jacobian determinant very easily as follows. There's a reference here in this expression to u, and right here in front of us, I can see that u is always between 0 and 1. It's right there in the picture of the pullback domain. Does everybody see that? Analogously, this v here, what can I say about v? Is v big? Is it small? Well, v is that axis, and you can see right here on the pullback domain, it's between 0 and 1. Is everybody happy? So, beautifully, what I've got here in dark blue is a number that's always less than 4. And subtracting 9, that means that this expression here, always less than or equal to, I suppose, -5. So it's always negative. Right? And being as it's always negative, its absolute value, right? The absolute value is the negative of itself. That's the thing about negative numbers. Their absolute values are their negatives. How we doing? But yeah.
Why does the stretching factor must be non-negative?
That's a deep question, as it turns out. Roughly speaking, this is good. I'm going to be very rough about this. Roughly speaking, this function here that we call a substitution function can kind of flip intervals backwards, and if it does, that will be reflected in the fact that these numbers will be reversed, right? And that's just because of the way we write down integrals. When we do it in the domain, we don't think about what you might call the orientations of the shapes. We just think, okay, well, all of these points land over here amongst all of these points. And if this function here were actually to be kind of flipping things upside down, changing the orientations, we wouldn't notice it like we do up here. And it's just the different way that we tend to perceive these things. So arguably, it really should be an absolute value here. We could say, hey, it's got to be an absolute value of this, and then also require that these have to stick to the convention of the smaller one on the bottom and the larger one on top. That would just be make work, though, effective in practice in this circumstance. Anyway, that's there's a much longer discussion that can go into a really full answer that we just don't have time for. But roughly speaking, that's the point. Yeah. Okay, I'm sorry, you had a question as well. Bianca, did you have a?
That was my same question.
Oh, okay, yeah. Perfect. Okay, yeah, good. Anyway, it's all over for the shouting at this point. Let me zoom out so I can get a bunch of stuff on the screen here. Let me clean up my mess. We are, believe it or not, almost done with this. So we've got our stretching factor. So dA, area in the XY plane, in other words. Stretching factor times du dv. Du dv is area over here in the UV plane. The stretching factor that we just computed, right there, as it should be. Right? And now it's just a matter of plugging in the little minor task of recognizing that, oh, well, everywhere I see an X, I need to put, well, what X is. So don't forget, X is given in the change of variables function. And so X is that. And then likewise, don't forget Y, also given in the change of variables function. And so don't forget to do that. Everybody happy? Roughly speaking, I mean, one way you can say this is that when it gets time to actually doing the algebra of it all, plug in, go ahead, it's fine. One little asterisk, just don't forget your stretching factor. Algebraically, in some sense, that's all you have to kind of remember. And it's very easy to accidentally forget that. So please prioritize in your process on this, that every time that you are doing a change of variables, double check that you've remembered your stretching factor. Okay, so what do we use as change of variables functions? In this case, this example that we just looked at, it was given to us. This was a warm-up example. It doesn't usually work out this way, that the thing you're going to use as your change of variables function is explicitly given in the statement of the question. Very often, most of the time, you might say you have to kind of dream up your own change of variables function. So just as a starting example, let's think about an example like, let's see here, let me draw a quick picture here. Suppose I have a circle that's centered over here like that in the XY plane. Let's just say there's my domain. And for whatever reason, and there will be really good reasons for this coming up real soon, I wish I could take this circle. Wouldn't it be nice if I could take that circle and just kind of shift it back so that its center is at the origin? That would be nice. And again, we'll capitalize on that being awesome real soon. But how would I accomplish this task? Well, what I would do, I argue, is I would view the existing circle that I was given as being the image of what I would like to pull it back to. Right? Now, how can I view this circle centered at the origin? What would I do to that circle centered at the origin to produce this circle that's centered up in the first quadrant there? And what I would have to do to it, of course, is I would have to push it that way. So the change of variables function, right? What the change of variables function has to do is kind of the opposite of what you want to do when you pull back. I mean, hopefully that's clear, right? The pullback is intrinsically backwards from the function that you're using as your change of variables function. Thus the name pull back, right? I mean, it's just right there in the name. Okay, so if you have, as I've indicated here, if your change of variables function adds a vector, then effectively what that does to your domain is kind of the opposite, right? And you'll find that pattern in anytime you're trying to rig up a change of variables function, you're going to find this oppositeness. Okay. So here's an example. I've got here a square, corners at these 4 given points, and a little bit of geometry allows you to plot this, and it's that square right there. So, all right, I don't want to have to deal with this as a domain. Corners everywhere. Whichever way I slice it, I'd have 3 different integrals to do. I don't want it. This is bad. Right? I sure wish that I could rotate my square clockwise. Wouldn't it be nice if I could rotate it clockwise? And I'm going to, in effect, rotate it clockwise by letting that be the pullback. That is, I'm going to have my change of variables function be a counterclockwise rotation. And the thing that I counterclockwise rotate to produce the given blue square, right, is effectively the result of clockwise rotating the blue square. Everybody see again the oppositeness happening there? So good news, easy geometry. This square over here has has a side length 2, and so after all of this rotating, the pullback domain also has side length 2, and it's again just about the easiest domain we can imagine. So big win. Everybody happy? Details to follow. We need to understand. Let me get rid of all the distraction here. I need to understand this counterclockwise rotation. I've commented on this before, so let me say it again, though, just as a reminder. I'm going to assume that y'all are proficient, well-oiled, and operational and everything, just clicking on all your old linear algebra stuff. Well, specifically, linear transformations, how to view them as matrices, understanding that the columns are the images of the standard basis vectors, and specifically how that applies to rotations and reflections and things like that. Again, if you're maybe a little shaky in that area, come to office hours. I'll be very, very happy to talk through that stuff with you. But that's what I'm doing here. I'm citing that this rotation, this rotation, T, counterclockwise, little geometry tells you what the angle is represented by a matrix like this, and understanding that the angle is pi over 6. Again, a little bit of geometry tells you that matrix specifically is that matrix right there. Is everybody willing to buy that? Again, details, make sure that you can follow those details. That's very, very important to be able to actually come up with that exact matrix on your own. Okay, so we've got our change of variables function. And now how do I compute the Jacobian determinant? Well, I've got to take the partials of x and y with respect to u and v. The usual formula. Don't forget that the change of variables function Yeah, okay, I'm doing it in purple now, I guess. The change of variables function tells you specifically the formula for x. And x is that dot product. And its partials are they. Right? And then furthermore, don't forget that y, again, given by the change of variables function, in this case, again, just the way matrix multiplication works, that dot product and its partials are right there. Is that cool? Little computation there for you. Anyway, again, most of that's linear algebra. Make sure that you're good with how to multiply out the matrix vector multiplication, and then you just have partials to compute the derivative matrix. And after all of that computation, the Jacobian determinant ends up being 1. What are the odds? Perfect exact 1. Seems a little surprising. Now let me try to persuade you this is not that much of a coincidence. What this is doing, this is merely representing how much areas are being stretched out by the act of rotating. Well, I guess technically we're rotating the other way. And when you rotate, areas don't change. Right? So from a geometric standpoint, from the question of, hey, is this a shocking result? No, it's not. This is exactly what we would expect for a rotation. Okay. All right. Minor side note, even though this is geometrically expected, you do have to show the calculation. Right? So think of this as an opportunity. If you end up doing a rotation as a change of variables function in your own work, consider the fact that the stretching factor should be 1 as a nice little confirmation that you did your calculation right. But you do still have to do it. Okay, and it's all over but the shouting. Again, the stretching factor is right here. Let's see, Jacobian determinant right there. And now, again, don't forget we have to plug in for what the x and the y are. X, of course, is that. And so this x right here becomes that right there. That's just plugging in. Likewise, y is this dot product right there, which means this y turns into that right there. And it's just a matter of writing it down. And you multiply some stuff out, and et cetera, et cetera. So, oh gosh, the original integral that we were given was this. We have now successfully pulled it back to get this. And I understand that at a quick glance, you might think, you know what, thanks very much, I'll keep the green one. But keep in mind that green one, this domain stinks. This domain is such that you're going to have to break this up into 3 separate integrals whose bounds are going to come from various lines that you'll have to find the equations for. There's a bunch of tedium that goes into this green one. I consider this to be pretty undesirable. Whereas this blue one, we have constant rectangular bounds on a single piece. It doesn't have to be chopped up into anything. And at a closer inspection, the only thing I really don't like about this integral is that these constants are I suppose I've seen prettier constants. Whatever. They're constants. It's really not going to be a problem. Right? So this is tremendous progress. This is a much more desirable integral. Is everybody happy? All right. Cool. Moving along. A couple of things that have to get said. I don't want to worry in this class too much about what I call regularity problems. But just as I do need to say this. Your change of variables function does have to be continuously differentiable for this to work, and it also has to be invertible. There's some sticky issues that come up if it's not invertible, and we're not going to encounter any real problems with either of these concerns in this class. Okay.
Why does it have to be invertible?
Short answer, you don't want to end up with a situation where you have a domain over here, which when you apply the transformation, you don't want the image to end up being, you could imagine this being sort of contorted and twisted around to produce, let's see if I can do this. Oh, gosh, I'm going to do my best. And I'm in the wrong mode. Okay, right, you could imagine taking your green rectangular shape, and if you effectively stretch it out and then twist it over itself, then you're going to have a problem with this stuff here. Effectively, you'll be, if this is part of your original domain, you'll be effectively counting it twice, because you'll see it over here as part of that, and you'll see it over here as part of that. So there's sort of double counting issues when the image overlaps itself in a non-invertible way. So it's this kind of thing. Again, we're not going to deal with any of that. Yeah. Okay. Sometimes the transformation will come to you backwards. So how do we deal with transformations that are backwards? First of all, let me remind you, if you have what we'll call the forwards transformation, the stretching factor says you look at the output variables, partials, with respect to the input variables. Right? Partial of the outputs with respect to the inputs. That's the rule. Okay. Now, let's imagine that you consider its inverse. Suppose, or for whatever reason, suppose you have a change of variables transformation that goes the other direction. Let's just say, the rule is the stretching factor is the partial of the outputs. U and V are now the outputs. Our change of variables function's we've drawn it that way. I mean, if you need to turn the paper around backwards, I guess you could, right? But the outputs are U and V, and I need to take their partials with respect to the inputs, now X and Y. Right? So I've got here two change of variables functions, and you can see that their stretching factors are given by these different formulas. Now it's tempting to say, oh look, this is literally the reciprocal of that one, because fractions and numerators and denominators and all that. But a quick reminder, this is not a fraction. This is a determinant. Determinants are not only not fractions, they're not even close to fractions. They're not limits of fractions. They're totally different critters, right? So even though we write it as a fraction, you cannot actually truly believe it's a fraction, because it isn't. But here's the good news. What we can say pretty much immediately is that if this were your change of variables function, if you were to do the one followed by the other, nothing happens. There's no stretching or squishing at all. If you just go there and come right back, and you just undo what you did, nothing happened. Right? And that said differently, though, in the process of doing that, you first stretched by that factor, and then in the continued process, you stretched by that factor. And so really, altogether, what we have is that this product is equal to 1, and that said differently, that these, in fact, are reciprocals of each other. What are the odds? Isn't that nice that these really are reciprocals of each other? So you actually can treat them as fractions. I mean, they aren't, right? But this is another one of those very convenient sloppiness situations. So nice little trick there. Let me show you an example of how useful this can be. Classic example. Suppose that my region is bounded by this pair of curves and this pair of curves. And you can see that between the four of those curves, there's this region here in the middle that's bounded by those four curves. Everybody with me? Suppose that's our domain for our integral. Well, again, corners everywhere. I don't like it. Right? Bummer. Nobody wants to do that. So how do we get around this? How do I do a pullback? And here's the clever move. Notice in this pair of equations right here. Now this is a clever observation, right? in that pair of equations, I've got a single expression, xy, that's equal to various constants. If I were to take that xy and call it u, then look at the lovely little result. The lovely result then is that I get u. Oh, man, I missed it. U is equal to these various constants, which gives me lines in the UV plane. Slick move. I wish I thought of it. I didn't. Somebody showed me this trick. It's real clever. So the way I want you to remember this move, this trick, is notice you've got to have constants here. Those need to be constants for this to work out, right? So said differently, your curves have to be written as stuff equals constant. In other words, the curves have to be written as level sets, right? But if you have your curves written as level sets, whatever you're taking level sets of, let that be u. And then likewise, in this other example over here I have xy squared equaling various constants. Let that be v, and then you get these lines. Real slick idea, very clever, gotta love it. And so again, we're in business. We have a given domain that we didn't like. We have a new domain over here that's a rectangle, which we do like, and it would seem that everything's in order, and let's go about our business. But then we have to recognize our function is going the wrong way, right? We're not pulling back through this. We are kind of pushing forward through this, and that's not how change of variables works. That's not how we've got it set up. So, okay, this is where we use this fact up here. I can find the stretching factor that I want. The stretching factor for the one that's going the correct direction, no problem. I just take the function that I have going the wrong direction, I take its stretching factor, and I take the reciprocal of it. Everybody follow? So yeah, cool, no sweat. And the algebra on this is actually pretty straightforward too. So again, looking at our change of variables function going that way, what you might call backwards stretching factor, the one going the wrong way, partials of u and v with respect to x and y, easy partials, easy determinant. The one that I want, the stretching factor for the correctly directed change of variables function that I can't write down, that I have not written down algebraically, just the reciprocal of that. Okay. All right. So, very nice. Excuse me. So, so it's a matter of plugging in. Here was the integral we wanted to compute. The differential, area differential gets stretched out by way of the stretching factor that I've computed. Right, here's our stretching factor here, 1 over xy squared. And of course the original integrand keeps coming along for the ride, and now a little bit of cancellation happens, and this grand total I can rewrite as that. But we do find ourselves in a weird situation now of this integral is not ready for plugging and chugging yet, because while I am in the UV plane, right, this is my pullback integral, all of this stuff here is not yet written in terms of u and v. And this is just the awkwardness of when the change of variables function goes the wrong way. Plugging in doesn't pull back the way we want it to because our function's going the wrong way. And so now we have the non-trivial algebra task of figuring out how do I get rid of these x's and y's. What is x that I plug in to get u and v? What is y that I plug in to get u and v? And notice I don't have that. I don't have x equals and I don't have y equals. Now, of course, you could, in this case, in this example, you could solve for x and y. Not hard. Totally doable. No problem. Let's not, right? I mean, I understand you could do that. What I want to point out, though, is the general idea of how to proceed here. And certainly there are circumstances where you cannot solve for x and y. So let's pretend this is one of those circumstances, even though it isn't. First of all, notice, technically I don't need to solve for x and y. I don't need to know what x is. I don't need to know what y is. I just need to know what x to the 7th times y is. Just the one thing. That's it. So don't bother solving for x. It's unnecessary work. And likewise, don't solve for y. Awkwardly then, what do I need it in terms of? I need to figure out how to write x to the 7th y. Oh man, I need to zoom out one more. In terms of u and v, which are these things. So let me say this all together a different way. I have a product of powers of x and y, and I need to rewrite that in terms of these products of powers of x and y. So that's the specifics of our circumstances. I need to figure out what do I do to products of powers of x and y to produce a specific different product of powers of x and y. And my proposal is hopefully believable. And this is just an algebraic appeal, but I should expect to have to take some sort of product of powers of these products of powers of x and y to get my product of powers of x and y. So this is just an algebraic appeal. I mean, if I gave you the green and asked you to produce the orange, would you be thinking about applying trig functions? No, of course not. I mean, what would you expect to do to the green to produce the orange? Something along the lines of what I have in purple here. It's a speculation. It's not a proof. It's just a speculation. But when you speculate accordingly, you multiply that out. You realize in this case that means that, well, apparently a plus b is going to have to equal to 7. Right? And apparently a plus 2b going to have to equal to 1. And so we can just do it. Right? I can figure out what a and b are just by literally solving in here for a and b. And keep in mind what those a and b are these powers of u and v that produce what I have. So annoying algebra that has to get done in this case, but that does resolve the matter, and this is, therefore, this is what you put in there to produce your final uv integral. Okay, so it's always different. Every time, now, so, I speculated here, let me get rid of the mess. I speculated that the structure I was looking for was something like this, and that was pure speculation based on what I was looking at. Depending on the specifics of the question at hand, it's going to look different for what you're doing. Right? Always different. So tailor your form to the details of what you've got to work with. Okay. All right. Now, real quick, and I wish I had more time to talk through this question, but I apologized in the recording that y'all listened to for the fact that I was just going to write down the formula for the stretching factor, and I just wrote it down, and we'll talk later about where it came from because we had so much other stuff going on, and there's too much confusion already. We'll deal with the formula later. So here we are. Now that we've got a few wins under our belt with change of variables and dealing with the stretching factor and going different directions, etc., I think we can give a moment to this. And the idea is actually pretty straightforward. If I've got a piece of area in the UV plane, it's easy to write down these edge vectors. And if I want to know what the images of those edge vectors look like over here in the XY plane, those images, well, we're taking images of vectors. We're taking images of input changes. The things that you do to input changes to get output changes is you multiply by the derivative matrix. That's the whole point. This is the big lesson, you might say, from chapter 2, is that input changes to output changes, in this case, input vectors to output vectors, the relationship is by way of the derivative matrix. So, that noted, I've got here now formulas for my two edge vectors. I can then compute this area by the usual formula, area of a parallelogram, right? It's the determinant of the matrix that I get when I make the columns the edge vectors. That's chapter 1 formula. Now, so we've got this monstrosity to deal with. How do I simplify this? Well, good news. I have here a scalar factor. du, it's a scalar. It's just a scalar. Factors right out. Likewise, this dv, scalar. Factors right out. And then the tricky bit, this is really cool. Let's think now about this. Oh, let's see here. Let's look at this column right here. What can I say about this column? It's what I get when I multiply dg times the first standard basis vector. Wait a second. What happens when you multiply a matrix by a standard basis vector? You get the corresponding column of that matrix, right? So this product here, this says, let's take the first column of dg. Let me say that a little bit differently. The first column of the matrix we're interested in is the first column of dg. Let me say that one last time. Same exact statement, slightly different phrasing. The matrix that we're interested in has the exact same first column that dg does. And analogous argument, this is the second column of dg. The matrix that we are interested in green here has the exact same second column as dg. And so therefore this matrix is exactly just dg. Wonderful little fact there, little observation. Okay. And we're done then. So we win the area that we're looking for over here. This output area, right? dA is relates to this input area, du dv, by a factor, and the multiplicative factor, the thing you multiply by the green area to get the blue area, our stretching factor is that formula that we previously claimed. So, works out really nicely. Yeah, there we go. Okay, three-dimensional change of variables. Good news. Oh, yeah, question.
I have a quick question.
Yeah.
Going back up.
Yeah.
What, can you, I'm still a bit confused why you have like the base unit vectors E2 and E1 multiplied by dv.
dg. You mean like this right here?
Yeah.
Oh yeah, I just needed to produce a vector that represented this edge of this little rectangle here, and I'm going to tell you what that vector is by telling you its magnitude and by telling you its direction. Right? So the direction that this points is, well, it points in the E1 direction. Right? And that's a unit vector. And because it's a unit vector, I can just multiply by the magnitude, and the magnitude says how wide is that rectangle, and that width is literally du. That's, when I chop.
So is that rectangle representing some point?
The rectangle is, it's going back to the very beginning over here where we were drawing pictures like this. We're talking about this rectangle right here. Yeah. Is that cool?
Yeah.
All right. So yeah, good news. 3-dimensional change of variables. Same story. I mean, very, very, very much the same story. You can imagine undesirable domains, and one could imagine, fingers crossed, hope that it works out, that I can view those undesirable domains as being images of, hopefully, much nicer domains, right? And wouldn't it be nice, having done that, if I could do a pullback and turn the unhappy green integral into the much nicer blue integral? Wouldn't that be lovely? The answer is, yeah, sure, go ahead. You just need to understand the stretching factor. That stretching factor that you get, totally analogous formula. It's, again, absolute value of the Jacobian determinant. This is how it works out. There's a lovely argument for this. It's morally identical to this argument. Again, I think this makes a really healthy, I would call it a practice problem or personal exercise, whatever. Figure out how to take this argument here for a 2-dimensional stretching factor. How would you adapt this? Very, very similar. Very, very similar. But in a 3-dimensional context, how would you adapt that to justify this 3-dimensional result here? Okay. And again, handy-dandy notation that I like a lot. Okay, so how do we use this? I'm going to start with a quick aside, and that is when you have a linear transformation represented by a matrix, surprisingly, the derivative of that linear transformation is represented by the exact same matrix that represented the transformation itself. Seems a little weird. Seems surprising that it would work out so nicely. How does that even work? I'm going to try to persuade you of this plausibility argument. Well, I'm going to try to remove the disbelief, at least, by pointing out this easy example. Let's just think about a single variable example. If t of x is equal to 3x, well, this is a single variable function. Straight up, single variable. I can talk about its derivative as just, well, it's t prime. And it's just 3. Right? Super easy derivative to compute. But if you were to take a linear algebra point of view on this, this is the matrix representing that linear transformation, and the derivative is the same matrix, if you will. So, again, kind of believable. Okay, good exercise, though, to check this fact on your own. It's very doable. All right. So, okay, with that said, here's the 3-dimensional change of variables that I want to deal with. This is a hard problem. This is a monstrously hard problem that's going to turn into a super easy problem. By way of change of variables. We're starting with our domain as a parallelepiped. It's this thing here. That thing there. It's the parallelepiped defined by these edges and a corner at the origin. So we've got these 3 edges. If you give me any 3 vectors in space, independent, let's say, then they define a parallelepiped. Yeah, everybody good? Okay, so that's our domain. You'll notice that's our domain for an integral. And before I show you the trick of how to get around this problem, let's take a moment to recognize what a nightmare this would be, doing it sort of, just rectangularly slicing it up in the usual way. This would be a nightmare. As follows. This parallelepiped has 8 vertices. One's going to be the start, one's going to be the end, whichever way you slice. That means there are 6 vertices in the middle. That means this is 7 separate triple integrals. Now right there, I think I've probably made a sale that we don't want to do this, right? Okay, 7 separate triple integrals, and here's where it gets worse. Those cross-sections, at best, those cross-sections are triangles. And given that this is probably some cattywampus, angled, weird parallel, they're not nice triangles where one of the sides is horizontal. They're tilted at weird angles, which means that each one of those cross sections has at least 2 separate pieces. And by the way, it could be much worse. Sometimes a cross section of a parallelepiped is a hexagon. Not even all that rare. That happens all the time. So this is a nightmare problem. Nightmare. Does everybody see why that's brutal, right? All right. So not cool. Here's the move. Here's the slick move. Again, I wish I thought of this. Again, I didn't. Somebody showed this to me. It's a cool trick. And one of the big tricks in math is to capitalize on the great ideas that other people have come up with. So the trick is this. These 3 vectors that define the parallelepiped, make those the columns of a matrix. Let that matrix define your change of variables function. That's the trick. That's the move. And if you do this, I claim that the pullback. Now, keep in mind, we were looking at this this nasty. If I can get this thing to, we were looking at this nasty parallelepiped there. The pullback is going to be just a unit cube. Just the unit cube. Everybody's favorite domain for a triple integral. Unit cube. Okay, now let me try to persuade you that this is true. I mean, I've made this assertion, but why is this true? Well, let's just think through what are the images of these defining vectors here, E1, E2, and E3, and we'll start with E1. What is the image of E1? I've got my change of variables function defined. The image of E1, I am going to be putting E1 right there, namely right there. What do I get when I multiply a matrix times E1? I get the first column. And by clever construction, that first column then is the first edge of the parallelogram. So the first edge of the pullback, the acclaimed pullback, is the first edge of my actual domain. And likewise for E2 and E3. So you can see that that means that the full pullback is that unit cube that produces this parallelepiped. So real nice move, and that's the trick. Make sure to always follow this trick in circumstances like this. And now again, it's all over but the shouting. We've got our change of variables function. By the way, not hard to find the stretching factor. I've got to do that whole thing. I've got to take the matrix and take the Jacobian determinant. Oh, good news! I don't even have to compute the I don't have to compute the derivative matrix because the derivative matrix. Highlighter mode. The derivative matrix is the matrix defining the linear transformation, namely that matrix whose columns are the edge vectors. So I already have the derivative matrix. A is the derivative matrix. And so all I have to do is take the determinant and it's all over but the shouting. Everybody happy? Okay, so now I'm going to move on now to a special category of examples of change of variables functions. And by the way, there's a real quick side note, cultural note. In many, if not most textbooks, the stuff that follows would be its own separate book section because we've done a lot of stuff so far in 5.5, right? There's a lot going on with change of variables and different kinds of examples and there's going to be a lot going on with what we're about to talk about, doing integrals in a coordinate system. We're going to talk about polar coordinates and cylindrical, etc. So it's a lot to put these all in a single book section. Anyway, it's an odd choice. Okay, so I'm going to kind of do all three of these together, just because they all work together very nicely. Y'all recall polar coordinates, and I pointed out I think it's best to think of polar coordinates as a function from r theta to xy, and different ways to think about it, but you can view it as it is literally a function. X and y are literally functions of r and theta. Likewise, cylindrical is a function and spherical is a function. Different algebra, different geometry, sure. We've got these three separate functions. Let's ask what would happen if I use these functions as change of variables functions. Well, sure. Not that big a deal. Go ahead. You can use any, certain regularity issues aside, you can kind of use almost any function as a change of variables function. And if I do, I compute the stretching factors, and so here's your Jacobian determinants. Now this is just algebra. I do think this is healthy algebra for everyone to do on their own at least once. It's not that bad, but it's a healthy exercise. So give that a try. I'll confess the one in spherical coordinates takes the Pythagorean identities are going to show up prominently, right? But as long as you don't let the notation kind of get out of hand, it's very reasonable. Okay, so you work those out, and here's your stretching factors. Your stretching factors are what I've got there. And now don't forget your absolute values. Very importantly, stretching factors are absolute values. But we don't like absolute values. They're hard to deal with in integrands. They're hard to deal with in general. Right? So here's where we're going to make certain choices. And I emphasize that these are choices. They're arbitrary, but they're very convenient arbitrary choices. And that is as follows. I'm going to say, look, I sure wish that this thing inside the absolute values was always positive. If that were always positive, then my stretching factor wouldn't have absolute values in it anymore. Wouldn't that be awesome? And all I have to do to make this happen is make sure that that thing inside of there is always non-negative. In other words, confine yourself to the right half, if you will, of the r theta plane. Just don't let r be negative. Is that reasonable? Now, I could have made this, give me 2 seconds, I could have made this choice long ago. When we first defined polar coordinates, I could have said, we don't allow r to be negative. But I didn't have any reasonable incentive to do that at the time. Right? And I think it's important to make concessions or arbitrary choices when you see the strong motivation for it. And when you have R positive, the really nice benefit is it makes your absolute values go away, and that's a lifesaver in doing change of variables. Yeah, you had a question.
So you're talking about choosing the sign of R.
Mm-hmm.
How can we choose R?
So what I'm saying is when you set up a change of variables using this as your function, just you always have different ways that you can represent points in polar coordinates. You kind of get to choose which polar coordinates you want to use. And I'm just saying make this choice that leaves R always positive. Yeah. Okay. So likewise in cylindrical coordinates, I want R to be positive so that the absolute values goes away. Arbitrary, but very convenient, and hopefully this is a reasonable motivation. Now, the tricky bit is with spherical. A lot of people get this wrong. I've seen this, especially students who have had high school multivariable courses. A lot of students think, okay, well, wait a second. R is the polar thing that has to be positive. spherical rho is kind of like I guess rho must need to be positive. Maybe I can make the absolute values go away by requiring rho to be positive. But if you look at the algebra, it just does not hold any water. Let rho be positive, so what? It was going to get squared anyway. Whether rho is positive or not positive makes no difference at all in the concerns we have about absolute values here. So it's got nothing to do with rho. The point here is we need for sine phi to be positive or non-negative, right? So that's the thing that's going to make the absolute value go away. If I can ensure that sine phi is positive, and of course that's easily realized. Just choose phi to be between 0 and pi. That makes sense. And now I have the really good news. The really good news is these are my favorite values of phi anyway. Right? I'm pretty unhappy anytime I have to use a phi that's outside of this. I think of phi as being the angle from the positive part of the z-axis. Negative phis are weird. Right? Phis that are like greater than pi are weird. So what this is saying is, don't do stuff that you shouldn't want to do anyway, and then you get the benefit of not having to deal with the absolute values that you didn't want to deal with anyway. It's win-win. Right? So this is all good news. All right. Let's see an example. All right, so let's suppose that here's my domain, the first quadrant portion of the unit disk. So it's this right here. And I want to compute apparently this integral right there. And before I get into the clever move here, let's recognize what a nightmare this integral would be if you were to crank this out in rectangular Now, the usual, if you were to just take a deep breath and slice it up a la section 5.2, 5.3, whichever one it is, right? Then this would be ugly. Look specifically now at this integrand here. That has exclusively even powers of y. That means when you do the dy integral, you're going to have odd powers of y, into which you will be plugging square roots. Square roots raised to odd powers leave square roots as residues. And that means that altogether, when you are looking at this, all of that as being the integrand for your outside dx integral, that outside dx integral is going to have square roots riddled throughout it. And nobody likes that, right? That means we're going to have trig substitutions or something annoying like that. So I just want to recognize that this integral that we've been asked to compute, if you were to go at it sort of, head on, this is a bummer of an integral. Okay, so now let's think about how to use polar coordinates to deal with this. I'm going to do my usual and use the polar coordinates function as the change of variables function, and I argue as follows. Let's think about this line segment right here. This line segment starts where r is equal to 0. It stays on the line where theta is equal to 0. And it goes from the origin to, where r equals 1, which happens to be, right there. Okay, so let me, just to clean it up, this edge, its image is that edge. Now let's look at the next edge here. Let's look at that right there. That is entirely on the line r equals 1, which is a circle. It starts at theta equals 0 and it goes to theta equals pi over 2. So it starts at theta equals 0 and then it goes and ends where theta is pi over 2. So that edge has as its image this edge. And you can keep tracing it around. This edge is that. And then the tricky one, this entire edge here, that entire edge has r equal to 0. That entire edge gets pinched down to just a single point. But the nice punchline is that this disk that we're actually interested in is the image of this rectangle. Everybody all right? Okay, so we've got a change of variables function. We've got a pullback domain. We know the stretching factor, right? So areas over, let's see here, areas over here, stretching factor times areas on the left. So r dr d theta. There's our stretching factor, this r right there, previously discussed. Notice I'm obeying the convention. R has to be positive. What non-negative? R has to be non-negative. So, granted, right, in my choice there, pullback. A little algebra, x squared plus y squared is just r squared. That's standard fact of polar coordinates, and we're in business. Look at this. I've got an easy integrand. My integrand is r cubed altogether, right? Easy antiderivative with respect to r. Oh, I've got constant bounds. You gotta love it. Everything's good on the left. This integral falls apart conveniently, pulling back through polar coordinates. Everybody happy? This is a slick move. This is a really nice idea, powerful idea that gets used a lot. This is a very common choice to use polar coordinates as a change of variables function. Everybody good? Okay. So now let me tweak this a little bit. I'm going to kind of streamline the process that we just talked about. Actually, let me come back up here for a second. When I started writing down these bounds that came from our pullback domain here, anytime you're turning a domain into bounds, there's this slicing process. And so the very first thing that I did is what I'm going to call theta slicing. So I was slicing perpendicular to the theta axis, and these are theta slices. They are, as they should be, perpendicular to the theta axis. And that's what theta slices look like in the r theta plane. So I'm just going to make the modest observation that these theta slices in the r theta plane, I can totally see what they look like right here in the xy plane. Each one represents a constant value of theta. Let's take this one here, for example. That says theta equals 0. Cool. This one here says theta equals a slightly larger value. Okay. Here, theta equals another different, slightly larger value. Cool. And just as you keep going, you're getting higher and higher values of theta, which just gives you slightly different rays emanating out of the origin. So the big idea is that while, yeah, sure, you can do your slicing of your r theta pullback domain in the r theta plane, you don't have to. You could instead say, I can see the entire slicing process right here in the xy plane. So go ahead. Why not? It's easier to see in the xy plane. Let me show you an example. Now, this is the exact same example that we just talked about. First quadrant portion of the unit disk, integral of x squared plus y squared. Exact same example. So here's the domain. Now here's the pullback that we talked about, but you'll notice I have this crossed out. Right? I'm going to point out how we can do the pullback change of variables process without actually drawing or even conceiving the pullback itself. So it goes like this. I've got my change of variables function. I know what the stretching factor is. That's the R. So dA is RdR d theta. That's just because I know the formula for my polar coordinates change of variables function. The stretching factor will always be R. That you don't even have to show that work. That's just already established. And now there's the question, though, of what's the range of values of theta. I've got to figure out what are these theta bounds. And again, I suppose you could imagine this process over there in the r theta plane, but then you'd have to draw the pullback, and you'd have to think through, well, wait a minute, what does that pullback look like? And that's effort, and very often too much effort. So I can just see the theta bounds right here in this picture. My theta slices look like this. The first one is there, where theta is just clearly 0. The last one, as I continue doing more and more theta slices as I go around, the very last one happens, if I can clean up my mess, there, vertically, where theta is pi over 2. So, boom, 0 to pi over 2. I didn't have to refer back to the orange scratch out stuff at all. Is everybody with me? Then likewise, now we fix a value of theta. So we're gonna fix theta. Let's say arbitrarily that one. Now, okay, to be fair, yes, there is a theta slice in the pullback. Fine, and I could ask, what's the value of R at that starting point? What's the value of R at that ending point? I suppose I could, but why bother? I can see that starting point right there. I can see that ending point right there. So much easier. And at this starting point, perfectly clear what R is at that starting point. It's the origin. R is 0. And at the ending point, well, I'm on the edge of the unit disk. That means that R is 1. Everybody good? I get the exact same polar coordinate integral I would have had I actually viewed it as literally as a pull back to a new domain in the r theta plane. But yeah, I don't. That's geometrically, artistically inconvenient, right? And so what we're going to do instead, and this is how business is done, by the way, if you're going to do an integral using polar coordinates as the change of variables function, we just have to make sure to remember to insert R as a stretching factor, and then just slice theta slices and R slices the way they look in the XY plane. And in practice, again, day in and day out, nobody in practice draws that. So this is what we mean when we say doing the integral in polar coordinates. In polar coordinates is code for I'm going to pull back through the change of variables function given by the polar coordinates conversion formulas. It's just so much easier, though, to say in polar coordinates. Okay, another example. This is a quickie. Suppose our domain is, let's see here, this whole solid unit disk here, right? And okay, well, theta slices and all that, but I'm going to view it as starting there, and that my theta slices just go all the way around and end when I get back to where I started from, and that has theta going from 0 to 2 pi. And then for any given value of theta, we fix an arbitrary theta. Now for that theta, let's see here, theta. What's the range of values of R? Well, we start at the origin. That's where R, of course, is 0. And we end at that point. That's on the edge of the unit disk. That means that's where R equals 1. Everybody happy? Okay. Cool. Alrighty. Yeah, okay. So, and the details to compute, that's all the same. Okay, hot tips. These are very helpful. You could slice in either order. You could do d theta dr. It's practically never better that other way. It might be a draw. It might be equally convenient either way. That's, yeah, sure, it doesn't matter, knock yourself out. That happens plenty. But d theta dr is practically never a better choice. So my rule is, I put the almost here as just kind of a, again, in my own self-defense. But in practice, just don't even entertain the other option. Just always use dr d theta. Don't ever do d theta dr. And God, it would be such a weird circumstance. I have no plans to create scenarios where d theta dr is necessary to solve the problem. It's very, very weird and unnatural for that to happen. Okay, so always dr d theta. Now, a psychological trick. It is very tempting to write down dr d theta. Like you could imagine, doing a process like this, and you're like, okay, well, I've got, let's see here, I've got a bunch of stuff I'm going to have to figure out. I know that we start with dr d theta as our differentials, and it's tempting to just write down the dr d theta by itself. And then, okay, now I got to fill in all the other stuff as we go along. This is a dangerous idea. The thing is, that dr d theta will always be multiplied by the stretching factor. I urge you to always include your stretching factor as you are writing down dr d theta. In other words, don't write down just dr d theta by itself. After all, that's not a thing. dA, the thing that we start with, is not equal to dr d theta. It's r dr d theta. So write down the whole thing. If I can get this to erase. Write down r dr d theta all at once. You'd be surprised how easy it is, if you don't follow this rule, to accidentally forget to come back and include the r. It is frustrating, super frustrating. I've done that a bazillion times myself, until I came up with this. I rigidly hold myself to this rule now. I do not write down dr d theta by itself. I always write down r dr d theta, to the extent of my ability to follow my own rule. Right? And it makes it to where you won't accidentally forget. And again, without this rule, I'd say probably a fourth of the papers that I see on exams forgot the stretching factor. Now, who cares, right? It's a minor thing. It's just one little factor. Not so. This factor, this one little r right there, that is, after all, the stretching factor. That's the thing that makes it all okay. That's the most sophisticated idea in the whole concept, right? Plugging in x equals r cosine theta, that's a real simple, that's just algebra. That's just, I'm going to take this thing here and I'm going to stick it right into there, right? That's not a deep point. It's not a sophisticated point. The r is the big idea. It, therefore, unavoidably has to count for a lot of points in grading, right? It just is. So this is actually, you can think of this good news, bad news. I like to think of this in a optimistic, glass half full kind of a point of view. But this one little factor, you can view that as you're going to lose a lot of points if you don't include it. Glass half full. You get a lot of points just for not forgetting it. It's free money, right? So, and as it should be. I mean, again, it's an important point. This is a sophisticated idea. That's what makes multivariable change of variables work, right? So, view this as a positive and make sure not to forget. Please, please, please. Okay. All right, and then the last thing, let's see. Oh my God, we're long out of time. But the slicing process is going to be just like before. Well, so we'll proceed with examples next time. All right, see y'all later. Have a good day.